那么现在我们进入下一个阶段，我们下一个阶段的话，就是我们下一位演讲嘉宾的话是来自于德国秘密Hearing的声学工程师 Omid。那么还是跟以前一样，我们会采用的是一个录播的形式，把这个他视频录播，然后加一个中文字幕。但是他现在已经在线了，所以稍等一下他会参加我们一个在线的一个 Q&A 的问答环节。那么稍等一下的话，桑老师会帮我们做一个问答嘉宾，帮我们那个观众跟那个嘉宾之间做一些回答跟沟通的一些工作。OK， 那么他今天演讲主题是基于消费类音频产品的听力评估和增强方法。那么呢，他个人是柏林工业大学的音频通讯博士，主要研究领域包括心理声学、声音信号处理和基于言语可懂度的空间音频处理，拥有超过10年的声学工程师经验。目前在秘密Hearing负责声音增强解决方案的研发。好的，那么在这个介绍之前的话，我还是会想对咪咪做一个简单的介绍，因为我相信可能很多做研发的小伙伴可能是认识他的，但是特别对听力学的或者是做验配师这边来说，可能了解的并不多，所以我们简单的介绍一下咪咪的一些情况。那么咪咪的话，其实它是一家来自于德国的公司，它是通过做测听的 APP 起家。那我们可以看到这个屏幕上面显示的这个测听 APP 就是他们最新版本的一个测听的 APP， 他们在整个 UI 啊，在设计上面都做得非常的好。那么的话，他们在测听，在完成用户的这个听测之后的话，他们可以以消费音频产品，包括音乐耳机、电视机还有音箱进行一个结合，能够为消费者提供一个个性化的一个聆听体验。那么根据他们官方的数据的话，他在3年期间在全球完成了150万例的测听。那么所以说其实这还是一个他们还是获得了很好的一些测听的一些结果的。那么的话，所以他们也一直强调是说我们是一个健康与个性化聆听体验的桥梁。那么的话，他们可以跟多样化的一个硬件平台进行结合，所以我们刚才说的，不管你在耳机啊，很多地方上面其实都可以看到他们的一些测听的一些小工具在其中应用，用来改善一个用户听音乐的一些体验。那么的话，我简单介绍完之后的话，我们把这个屏幕交给甜甜，甜甜你播一下视频吧。
In the first part, we will focus on the hearing screening, on the different testing methodologies that we have developed, and also on the limitations that we see there. The second part covers the hearing loss compensation that we have developed for the consumer audio space. So let's start with hearing loss. When it comes to hearing loss, there are a couple of different symptoms. One is raised absolute thresholds. This means a reduced ability to detect very faint sounds. Related to this is also the abnormal growth of loudness. This is a reduced ability to lower level sounds, but a close to normal ability to detect medium and high level sounds. There's also a reduced auditory tuning, meaning a reduced ability to detect simultaneously played back sounds at different frequency ranges. And as a fourth aspect, also reduced temporal processing. So let's continue with our pure tone threshold PTT testing. What we are measuring here is the pure tone threshold, basically, so the sensitivity or the playback level that is required for a person to detect a sound in more than 50% of the cases. This is more or less the gold standard in like audiologic practice, like when you go to a clinician or to a lab to examine your hearing. Basically, this is the methodology that is applied to examine your hearing. The ISO 8253 basically prescribes the instruction how the methodology is to be performed, specific requirements on the testing devices and also on the testing environment. This is very well defined and like used as the standard metric and standard procedure as of today. When we developed our pure tone threshold test for iOS here, we had to make sure that we meet those like requirements. And one of the most important requirements is this calibrated devices, the last point on the last slide, basically. In a laboratory, you have calibrated devices, like as shown here on the left side with a calibrated audiometer. So for us, in order to offer this test to the consumer audio space, we had to make sure that we offer a set of calibrated devices. This is what we are offering for a couple of headphones and the iOS platform, basically. So how did we get there? Basically, we followed the standard and applied screening. So we screened our user base and invited users here. We screened them on their hearing ability, and then we selected a subset of those for our calibration purposes. We explained the procedure, what will follow, what tests will they do, etc., etc. Then we took like a couple of audiograms using the calibrated audiometer, here termed as reference, for each and every individual of this user group. On the other hand, we tested those same users using our device under test, basically. In this case, what you see here, the AirPods Pro and the iOS test. This was done multiple times, as especially for these in-ear devices, there is quite some variance that is introduced due to positioning and other factors here. Once we had those measures, we could compare them actually. So we could compare the reference to the collected data of our device under test. And by comparing, evaluating, and analyzing this data, we could derive correction factors for this specific device combination. And by this, we can offer now like this combination as one of the calibrated sets for our users using the iOS platform. So you might wonder, like, how good is this? And when we developed this, we did quite some testing, but of course, never like be too sure. And therefore, we are quite happy actually with a very recent publication by the Johns Hopkins Medical School, where they evaluated exactly this. They tested how good our results, or the results of our iOS test basically is compared to the gold standard audiometry. So they invited like 50 users like of different hearing ability. The people took the test in a controlled environment, took our Mimi hearing test, and they took also the standard audiometry. And in the end, they compared how close the Mimi hearing test can go to the standard audiometric results. What they found out is quite remarkable, also makes us quite happy. We see here the results, the raw results they plotted, also shown in the publication. And to make it a bit more clearer, I will briefly explain the plot here. On the left side, we see for the left and right ear, the frequencies from 250 Hertz to 1 kilohertz. And on the right-hand side, the two columns are the frequencies 2 kilohertz to 8 kilohertz, also for left and right ear. And the plots, dots show the different data points. What is basically highlighted is what they also evaluated is the difference in results for our test and for the classic audiometry test. And ideally, this deviation is almost zero, or very close to zero, so that our test gives the same result as the classic audiometry test. I highlighted the mean basically in all of these plots a bit, so it's a bit more clearer. Please refer to the original publication for all the details of how they actually did this. What you can see here, like if you look close enough, is that the average is in almost all cases, it's very, very close to zero, meaning you get the same result of the classic audiometric test and our Mimi hearing test for a very different user group and very across a large range of different hearing abilities. We have also this data collapsed here in this table where we can see like more of the numerical, like, and how this translates to the numbers basically. The data is split now into 3 different groups: normal hearing, mild hearing loss, and moderate hearing loss. And what is shown here is basically for the left and the right ear, the mean PTA, the pure tone average. When we look at the differences between standard audiometry and MIMI hearing testing, we see differences that are close to 2 dB. Only in one case it's a little bit higher, but in the most of the cases it's very, very close to the actual audiometric result. This proves that the pure tone threshold test is very, very good, and a very good replacement also for continuous testing of your hearing ability, and especially if you don't have access to a clinician or an audiologist. But we do not only develop hearing tests, we also want to make sure that people get more aware on their hearing ability, that people engage with their hearing, and that they also know more about their hearing. This is why we partnered with the Johns Hopkins Medical School there, with the Cochlear Center for Hearing and Public Health, basically, on the initiative called Your Hearing Number. And the idea here is that every user, every person basically is aware of the hearing number, and the hearing number is here the pure tone average. So everybody in the future ideally should be aware what their hearing number, their pure tone average for left and right ear are. And to get your hearing number, MIMI hearing test is a very good solution. I mentioned this at the beginning. Let's look a little bit closer at the limitations that we are facing when we do hearing screening on consumer audio devices. Two aspects that are related to the playback device we see in this graph, basically. This shows the frequency response, so the output level at a specific setting of the device for a multitude of different headphones. Each headphone is reflected by one of those colored lights here. And what we see is that depending on what device you're using, what headphone you are using, the output level is slightly different. And if we don't know this in the testing procedure, and in most cases we don't know, this directly translates into your hearing test result, basically. So imagine you have 10 dBs of higher sensitivity at a certain frequency. This will directly result into a 10 dB offset of your actual hearing result at this frequency. Another aspect that we also see here, it's not only the sensitivity or the frequency response across the multiple frequencies, but also the overall sensitivity of the headphone, basically, meaning how much sound pressure is the headphone actually producing. And we see this for the blue curve here, that at the lowest plot here. This reflects a headphone that has a reduced sensitivity compared to the others, meaning if we don't know that your user is using this headphone, this will directly go into the hearing test result, and we might give them a false result, basically. So this is why the calibration is so important also. But in many cases, we cannot calibrate because we just don't know the device. Two other aspects when it comes to the environment and also the user behavior. So imagine a person using just they discovered their hearing test on their phone, basically, or in the App Store, and now they want to do the test, and they have zero knowledge about what is required to do this and etc. So it might be that the person might do this test outside, basically, and then there might be additional noise, like example in this image here. So the additional noise will directly translate to the hearing test result, basically. So as said before, we won't measure the hearing ability, but the hearing ability in this specific environment here. And then an additional aspect that we also cannot control, obviously, is the user attention, whether the user is paying attention, whether the user is doing something else while doing the hearing test. So this is also something that we cannot control here properly. To cope with some of these things and some of these limitations, we developed the mask threshold MT testing method. It's again a method to allow us to learn about a user's hearing ability, but it's slightly more suited to this consumer audio space. The method is like depicted very roughly here on the left side, meaning we have like a certain a masking noise, a narrowband masking noise at a specific frequency, and we have a pure tone running from lower frequencies to higher frequencies around this fixed masking sound. So the procedure is actually very similar to our PTT test. The only difference is actually that we are playing like this constant narrowband masker at the same time. But the task remains the same. The user is asked to indicate when they hear the beeping sound in presence of this masker tone. What we get in there is not an audiogram, but a mask threshold curve, basically, as you can see them also on the right-hand side. Here we depicted the masking curves for different levels of hearing ability, just to like highlight how different hearing abilities are reflected in those masking curves. So what we can see here is like for like very good hearing, these masking curves are quite steep. And the more hearing loss we have for this frequency that we are testing here, the broader the curves basically get. And from the shape of the curve, we can estimate the user's hearing ability. When we developed this test, we ran a couple of different tests just to make sure this test is working as it is designed for. And one of those tests is to test retest reliability. So the question here was, if a user does this test multiple times, does he or she get the same result again? And we see this here for the different users during our development of this test. Each subplot is one user and 1 ear of one user, basically. And the two different colored lines represent the two repetitions of the case, of the test. And we can see here that like the lines pretty good match up, basically, meaning that like whether they do the test once or a second time, they pretty much get the same result. And this was just one of the tests that we ran to make sure that like this is an objective test that can be done multiple times, and it provides a static and a reliable estimate of someone's hearing ability. Another limitation that we also focused before on was like the difference in frequency response of the different headphones. And this aspect I want to briefly show you here on this plot. What is shown is basically the mask threshold curves for one user, like just exemplary, but for using very different headphones. So there are headphones from Apple, there are Beyerdynamic, Sennheiser, a couple of different headphones using here. What we see is basically how the traces lay over like for the different headphones. And what we can see here is like that even though the user is using different headphones, the mask threshold curve remains pretty much stable, or pretty much the same. So this means even though there are slight deviations and differences in the frequency response of the headphones, the estimate of the mask threshold curve is pretty stable. So we can use this also for a multitude of different headphones to assess someone's hearing ability. One last aspect here that we also developed while developing checked was the sensitivity of the mask threshold to the actual playback level. So before we said, like in the consumer audio space, we typically don't know what the absolute playback level is. And therefore, we need to make sure that no matter what the actual playback level is, this procedure provides a more or less stable and accurate estimate of a user's hearing ability. We see this here for two individuals. On the left-hand side, a more normal hearing user, and on the right-hand side, somebody with hearing loss. The free traces basically show the repetitions and the reversal data that we collected for the testing methodology. And the free lines basically reflect 3 different levels of sensation level. So the lowest line is 20 decibel sensation level, the middle line is 30 decibel sensation level, and the highest line is 40 decibel sensation levels. What we see here is basically like the curves are shifting and are offset depending on the actual playback level. But what is more important for us, and also what we are evaluating, is basically the shape of the curve. And this shape of the curve stays pretty much constant, even though we are using like different playback levels here. So this is how we approach like the different limitations that we have in the consumer audio space, and we highlighted the benefits of using the mask threshold test for the consumer audio space and how it's able to cope with the limitations in terms of absolute frequency response, in terms of absolute level, and also in terms of retest reliability across different tests there. What I, in the end, want to focus on or quickly touch on basically is the hearing loss compensation technology that we are offering for consumer audio devices. Once we know the hearing ability of a user using one of our testings, we can basically provide an audio processing that compensates for this level of hearing loss. And we are doing this because we believe that using or listening to audio that is adapted to your hearing ability prevents you from making or compensating for your hearing loss in a way that is probably not the most healthy, meaning just raising the volume, for example. But if we precisely adapt the audio to your hearing ability, you will get a better experience and you will hear more of the things that you are missing without having to raise the volume quite much. And this also leads to like a better and more healthy long-term hearing, and you will develop less of additional hearing loss because of this like compensation behavior that you are applying. So our approach to hearing loss compensation was pretty much inspired by biology, basically by the auditory system. So we know there are like afferent and afferent processes in the brain and in the auditory system that basically control the way you adapt or your hearing adapts to different like acoustic scenarios. And we try to capture some of these aspects into our like compensation technology to reflect what the brain and what the auditory system is actually doing by itself already. And we do this by splitting up the signal into the different frequency bands, like as the basilar membrane is also doing. And then we run through a network of different compressive stages before we apply additional gain to the signal. And all of this is informed by the hearing ability of the user. The idea is that we have this complex network of compressive systems in place, and there's a forward path and a backward path to this. In the forward path, we apply compression to the very high intensity signals or the signal components in your signal that you're listening to, so like the drums or something like this. And we lower the intensity of those signals, so in order to reduce the masking effect of those, but also to reduce the dynamic range of the signal so that it better matches the dynamic range of your hearing. With this additional feedback loop, we can make sure that like this compressive behavior is actually adapting to the sound that you're actually listening to. So think of a situation where we don't have this feedback loop. We would need to know beforehand at what threshold your signal is coming in, where we apply compression and where the system is more linear. And And this is like mostly hard to do, if at all. And with this additional feedback loop, the compressive system basically adapts to the level and to the level trace of your system and of your signal, so that the compressor is more effectively working where it's supposed to work. And this allows for a more effective like restoration of normal loudness or close to normal loudness, and also applies to a reduction of auditory masking with our technology. So taking these components together, we believe that with this system tuned to your absolute hearing ability, we can very precisely like adapt the sound to and enhance only these parts that where you need enhancement, and leave the others untouched. To make this a bit more tangible in the end, I want to give you like a short overview of a demo that we put together, so that people can understand these effects a bit better, basically. What we put together here is basically it's an audio demo. And what you can perceive when you follow the link also, you can listen to different audio examples and excerpts, and listen to the audio files that is processed for different hearing abilities. So we have the hearing loss simulated for somebody with good hearing, somebody with average hearing, and somebody else with limited hearing, and we applied this hearing loss simulation to the audio files. In addition, we also pre-processed the audio with our technology and ran through the same kind of simulation loop. And so you can now perceive how hearing loss sounds with and without our technology. I will quickly show you how the demo works, and then you can like check it out for yourself and see the result and also perceive the effect of the processing. So let's follow the link here. The audio is loaded. There is a short like introduction. I will skip this video for now. You can watch it later. And at the bottom you have a big play button. With this you start playing the audio. At the top you have the enable or disable MIMI. And on the left-hand side you have the different hearing abilities that we simulated. And on the right-hand side, we have the different content types. So I will just like give you a short intro to this. You can play around with it later for yourself, but just as a first intro here. So I think this gave you just a short like introduction on what you can find on this demo page. Check it out for yourself. Yeah, that's about it. Thank you for your attention and for following this episode. And yeah, see you around.
Okay. Thank you so much, Omid. I know you have been online. And 我们这一个环节的话，我们那个因为涉及到比较多技术的部分，所以我们交给桑老师来做我们的一个问答嘉宾。So Omid, are you online? Can you unmute and open the cam?
Yes.
So let me see if I'm online. Okay. Hi, nice to see you here.
Sure.
Okay. 那么今天因为 Omid 的时间会比较赶一些，因为他大概再过14分钟，他要进入下一个会议。那么所以前面的部分的话，可能是 Omid 来回答。那后面在 MIMI 的话，这边他会有中国区的研发的同事也会来帮忙负责回答一些问题。所以有问题的小伙伴们抓紧赶快问吧。OK， 桑老师现在把时间交给你。
好的。 对，我看看咱们聊天的这个里面有没有任何同学想问的问题。如果没有的话，我先问一个。起个头啊。Hello, Omid. I just have one question regarding the mask threshold based test and the PTA test. I understand that basically they are supposed to address different problems, but could you elaborate on what exactly are the difference of the problems they are solving?
The Purotone test basically tests the lowest sounds you can hear, and the mask threshold test tests the sounds you can hear when there's another sound. And with this, we are testing more on the supra threshold level, so more on the level where you're also like listening to music. And we think that this is an advantage of the mask threshold test, because it's just like it's more at this playback level that is also for music and for speech. Interesting.
Thank you. Yeah, so my understanding is that for the threshold mask threshold based is actually to solve the problem of frequency resolution, in particular when the people have the hearing loss problems. So they are basically addressing, one is the loudness threshold, and the other one is about the frequency resolution for the specific.
Yeah, it's more related to the auditory tuning. It's true. Yes.
Yeah, auditory tuning. Got it. Thank you. Okay, I see there is one question to you. Could you explain how to reasonably compensate beyond 8 kilohertz or 16 kilohertz for high fidelity music? Okay, so that's about yeah.
尚老师那个问题回答的时候，可以帮忙做一下中文解释吗？
哦，对，sorry，对，刚才那个问题我是问了一下，就是这两种 PTA 的基于纯音测听和基于它这个 mask 的这个测听的方法的区别是什么？然后 Omid 的回答是，就是他们一个是解决响度的这个听阀的问题，是吧 ？PTA 我们都知道解决听阀的问题，然后基于那个噪声的这个噪声阀的掩蔽的测听，更重要的是解决就是当你在有噪声或者音乐的环境之下，到底这个增益就是这个特定频段的增益应该怎么加，就是解决当有环境背景声或者音乐的环境下面的时候，我的理解就是关于这个频率分辨率的问题。然后这个欧米得讲一下，这更多的是他刚才 PPT 里面提到的，是关于频率分辨率跟那个 auditory tuning。auditory tuning 就是在同一个频段上，当有多个 tone 的时候，多个不同的声音的时候，你是否能把它分辨得出来？只有听力损伤的人，他频率分辨率因为内毛细胞的这个损伤的原因，他可能听见了，他也分辨不出来。但是基于这个 mask 的方式，他就可以能把它分辨出来。这是我的简单解释一下。然后next question, yeah, can you see the question, Omid?
Yes.
On the screen? Yeah.
Like with music, we have like content above like 10, 12, 14 kilohertz, and our processing is designed to compensate up to 14 kilohertz approximately. And yeah, we have content there, and we can like also estimate from an audiogram, where we have data for 8K. We are testing with the Purotone test. We are testing up to 10 kilohertz basically the hearing, and therefore we can also like have an idea of how your hearing is at those frequencies, and then we can also compensate there for the hearing loss, because there is signal that needs to be compensated for, and we also know about the hearing loss there. So it's straightforward, like, but not above like 14, 15 kilohertz. There's nothing like in the signal, and we also don't have data there.
Okay. Yeah, audio translation. 所以欧米的刚才讲了，他们的测听最多就到14到15K 超过16K 其实是不会再测量的，因为超过16K 的话，其实对听损来说，这个其实意义就不大了对音乐的话也是这样子。然后so Omid, there one more question to you. Is there a limit of the hearing loss level of your solution? So for example, if it's a heavily hearing loss impaired person, could you still help? Help the user?
So when we get this question quite a lot, and we don't like say that there's a specific limit, but we say that there's like the effect or the improvement for people with very bad hearing is obviously smaller than that for people with mild or moderate hearing loss, and this is typically the range that we are covering. So basically everything from no hearing loss to a mild hearing loss is basically our main area, and where we can do most. And then with moderate hearing loss, people most often already have like a hearing aid, and this is then like not where we don't like combine this with the hearing aid basically.
And that's exactly why you position your product for the consumer products, right?
Exactly. Yeah, we see that hearing loss starts quite early, and it's good to like also compensate and act early, so you don't like develop a strong hearing loss, but you can already act on like already a slight hearing loss to prevent you from, as I said also in the talk, from adopting like higher volumes that you to compensate. And if you're listening at higher volumes to compensate for your slight loss, you are making it actually worse, and we are trying to address the hearing loss very, very early, so you don't need to overcompensate the level there.
Sure, that's clear. 所以他们这个方案就是正如Omid刚才讲的，对于这个轻度听损啊，玛雅的轻度听损是最好的。然后随着听损程度加重，可能带来的好处也会逐步下降，这个也很容易理解。就我问他，这是为什么？他们技术主要是给这个消费类电子用的。然后对于重度的来说的话，那更多是一个助听器要解决的一个问题啊。所以他们的最大好处就是对于轻度患者来说，你并不需要调大音量才能够听得清这个说话，是吧？因为它更好的解决了一个掩蔽的时候这个问题。它通过这特定的掩蔽，把掩蔽的噪声跟那个，其实你可以理解为分离网络，可以把这个你想听到的语音更好的分离出来，然后对噪声或者是背景的音乐进行一个一定的程度抑制，然后突出你想听到的语音声音，这样你就不需要把音量调得特别大，从而保护了你的听力啊。All right. Okay. Thank you, Omid. Last question. Is the mask ratio testing applied in all your tests, like in TV earbuds? Will you apply both together? Okay. Yeah. Okay. I mean, that's
yeah, we use the MT test for headphones, but we also use it in the TV product. Yes, that's true. And for the last question, we also like on iOS, we also offer PTT and MT together. So we also see quite some people who are interested in doing like both tests and then like to test like the different aspects of the hearing. And this is also very, very valuable for us. Yeah. But of course, like in the consumer audio space, it's always not very many people want to do a 2-minute or 3-minute tests, like and we have to balance the length of the tests always. And this is why we are offering this optionally. For people who are very interested in, they do it, but for most of them, they only do one of the tests.
By the way, which one is optional?
And you can just switch in, like if you download the app from the iStore, from the Apple Store, you can basically choose what test to do.
OK， 对，就是我们刚才讲，对他们 MT 的方法也用在了 TV 电视里面。然后对于消费类电子来说，消费类电子的用户来说，很少有人愿意做超过2分钟的一个测试，所以他们这个两种方法的话，你可以选其中一个，也可以两个都做啊。然后你自己下载的 App Store 上可以自己试一下。对，两种应该都存在于所有的产品当中啊。OK， any more questions from our audience? All right, I'll count to 1, 2, 3 for the last chance of raising any questions. 1, 2, 3. All right, okay, that's it.
Yeah,
thank you.
I want to ask a question about from a business part. So 我想问一个关于这个商业的问题，可能我觉得他们中国区的人可以回答。就我直接用中文来问吧。就是因为我知道其实咪咪这个产品还是蛮有意思的，因为它可以就是跟很多一些音频的产品结合在一起。然后我刚才看到留言区有人说他们已经有产品有量产了，所以我想看一下在国内的一个情况是怎么样的，是包括它这个跟硬件结合的难度有多大。Philip, can you help answer this question?
好的，是这样，就是大家可以听清我说哈。
OK， 可以，你说。
OK， 是这样，我们咪咪的这个算法其实目前已经量产的那个产品，就刚才也提到，就包括电视、耳机，甚至一些流媒体的 APP 端的一些应用。那这个其实因为产品它覆盖面其实现在也是在全球都各个区域都有嘛。然后国内的话，我们其实也有一些合作的客户，以及一些在谈的，也即将要发布的一些产品。 然后已经合作客户里边，其中我可以举个例，就是像Clear 这个耳机这个品牌是我们的合作客户，对他们的 TWS 的耳机，大家可以去搜一下，就是他们有一款叫 Ellie Plus 2这款型号的耳机，就带有我们的算法。然后其他的像一些其他的一些品牌的手机一些耳机也好，一直在洽谈当中。然后有一些部分可能是在明年年初会有一些会有发布，这个大家可以期待一下。国外的话，像国内的其实还有一个就是飞利浦电视，但它又是隶属 TPV 嘛。然后我们其实和 TPV 的欧洲这边的合作是非常深入的，然后达成了一个战略合作。那 TPV 欧洲在未来会有几十款电视的型号会合入咪咪的算法然后美国的Skull Candy 一个耳机的品牌也是我们的合作客户。Stella。
OK， 谢谢。宋老师你要说吗？有什么要说？
我没有，我觉得菲利普解释的挺清楚的啊。
对 ，OK， 我们还是蛮期待能够看到这套产品的利用。因为我时间也差不多嘛，我就最后讲一下，就是因为咪咪其实他刚才在 video 里边也讲到，他说其实他的目的不是说做助听器一个听力补偿，他更多的是说我能够通过我去了解了用户的一个听力损失的一些情况，然后我通过一些方法去做一些增强，就是把那些听力的部分给他做一些适当的补偿跟增强，这样的话可以让用户有更健康的方式去使用他们的音乐耳机或者是电视机或者智能音箱。所以我觉得基于这个出发点的话，所以这也是为什么咪咪在这么几年的发展当中还是获得了蛮好的一个进步。所以也是蛮高兴这次能够请到咪咪的人过来。OK，so 我看留言区应该没有任何问题了吧？如果没有问题的话，那我们就先结束这一趴的一个问答。OK，
谢谢。
So thank you, thank you, Omid, thank you for your time. And 还有刚才咪咪中国有来了2位同事做支持不好意思，这次没有让你们上线的机会，但是我们看留言区有没有一些可以继续回答的一个地方。OK，thank you so much. Thank you everyone for this session.
See ya.
Yeah.
Thank you.
Yeah, see you all. Bye bye.
谢谢。
OK.